In this section, we're going to talk about estimating a population proportion. So we learned that a population proportion is a statistic that comes from just a percentage, basically. And so anything that is given in a percentage is typically a population proportion. Like what percent of all cars are gray? And somebody might report that 27% of all vehicles on the road are gray. That is a population proportion because it's a percentage. So a point estimate is a number that we get from a sample that estimates the value of a parameter. For example, if we talk about all cars in America, and we want there is an actual percentage of all cars that are gray, but I'm pretty certain that nobody knows that exact percentage. But we can get an estimate by collecting a sample and figuring out what percentage of our sample is gray, and that gives us an idea of what the percentage would be for the whole country or whatever the population may be. All right, so the point estimate for a population proportion is what we call p hat. So p hat is x over n, and we saw that in that last chapter, last section actually. And so we have x, the number of individuals in the sample with the specified characteristics, all right? And n is the sample size. N is always going to be the sample size here. All right, so a quick example. So here we have a survey from the Quinnipiac University poll, and they surveyed 1,783 registered voters nationwide and asked how many are in favor of the death penalty. And 1,123 were in favor. So let's obtain a point estimate for the proportion. Proportion, again, is the percentage there. So our point estimate, p hat, is going to be x, the number 1123. That's the number of that said yes. And 1783 is the grand total. And punching that in our calculator, we get 0.6298 or 62.98%. All right. So about 63%. So what we want to work on now is finding what we call a confidence interval. So a confidence interval for an unknown parameter consists of the interval of numbers based on a point estimate. All right, so it's based on a point estimate. So we would be unwise to take this statistic and say, oh, since this study was done, I know for sure that 62.98 of all people in the United States are in favor of the death penalty because this survey here said so. Well, this gives us an idea. That's a lot of people, 1783. But we can't say that for sure. Now, we can be fairly certain that the national average might be close to this. And we need a way to figure out and say, well, the national average, there really is a national percentage. And it's probably somewhere, I don't know, maybe between 60 and 70, or maybe between 55 and 65. I don't know. So we need a way of saying what that range is, so we can have an idea. And we have what we call a level of confidence. So a level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. All right, so just to kind of get some framework here, the idea is this. We want to, you can imagine like making a newspaper article. We want to say I am, and we're going to have a percent, maybe 90% confident, ... that the value, the percentage, let's say, the percentage of people, let's say Americans in favor of the death penalty for in cases of murder. I think that's what it said there, for persons convicted of murder. Okay. And we want to say between, and we want to have two numbers. All right, so that's kind of where we're headed. What are the two numbers? Well, I don't know. Maybe it's maybe we could say 50% and 70%. That's a pretty wide gap here. We'd like to be more precise than that. All right, but we want to be able to make a statement something like this. All right, and how do we come up with this level of confidence? All right. And how do we come up with these numbers? That's where we're headed. All right. So, for example, if we have a 95% confidence level, we're going to say alpha is 0.05. All right. Because the level of confidence, we're going to say 1 minus alpha percent. All right. Alpha, that's the Greek letter alpha there. All right. So it's basically take 100 minus the confidence level, and that gives us our alpha. Right. So if we have a 95% confidence level, that implies that if we 100 different confidence intervals were constructed, each based on different samples from the same population, we would expect 95 of those intervals to contain the parameter and 5 not to contain the parameter. Well, okay. What does that mean? Well, there's a real number, a real value of p that exists. In this case, p being the number of the percent of people that are in favor of the death penalty for convicted murderers. All right. So that it really exists. All right. Now, what this is saying is, if we were to have like a number line from 0 to 100%, okay, or let's say from 0 to 1.0, that's a little more accurate, okay? So if we pick our interval, let's say from 50%, 0.5 to 0.7, like I said up top here, okay? If that was a 95% confidence level, another way of saying it is where there's a 95% chance that this true p-value that we don't know actually falls between 50 and 70, or 0.5 and 0.7. So there's a 95% chance that the true number, which we don't know, falls in between there. Okay? So how do we get that interval there? Well, what we're going to do is we're going to take our point estimates and we're going to add and subtract a margin of error. So we're going to start by our estimate that we get from our survey, and then we're going to add and subtract a margin of error. All right, the margin of error of a confidence interval estimate of a parameter is a measure of how accurate the point estimate is. All right, so it kind of tells us how accurate it is. So we're going to say, we have this survey here was 62. What do we say there? It was 62.98, 0.6298. So 0.6298 lives in the middle here. And we're going to go up and down a little bit, and that's going to be our error. All right. So we're going to go up and down a little bit. We're going to add and subtract the error from our point estimate to get these two boundaries. All right, that's where we're headed. So how do we find the error? We're going to figure out how far up and how far down we need to go to get these two boundaries, which my example was 0.5 and 0.7. All right, which are not the same distance away from 62, but we'll see that it will be the same distance in the future. So how do we find the margin of error? Well, there's a few things that play into the margin of error. The level of confidence, all right? So the level of confidence is something we're going to decide. How confident do we want to be in our numbers? The sample size. As the sample size increases, the margin of error decreases, okay? So let me back up here. As the confidence level increases, the margin of error also increases, all right? If you want to be super confident, let's go back to our little example here. If you want to be super confident that you have the true value, 0.62 was our estimate. If you want to be super confident, then I might go, up 30, which we put us at 0.92, and down 30 or 0.30. That would put us at 0.32. Now that is super wide, this interval from 0.32 to 0.92. But I could say that we're very confident, the confidence level will be very high that the true p-value that we don't know, that true p-value is probably somewhere between 0.32 and 0.92. All right, so I would say that this would be close to like a 99.9% confidence level. I can say I'm very confident. There's a high probability that the true value of p falls between 0.32 and 0.92. All right, if we have a bigger sample size, then the margin of error decreases because our estimate will be better. If the standard deviation, if it's more spread out, then we'll need a wider interval for our level of confidence. If the numbers of the in the data items are more spread out, because that means a higher standard deviation, then we'll need a wider interval. Okay, so what's this alpha we speak of? All right, so alpha is the amount of error we want. All right, so we want to allow, that is. If we want an interval with a given width of 1 minus alpha on a standard normal distribution, then the number alpha is the area outside, and that's the key. Alpha is the area on the outside. Or we can say 100% minus the confidence level percent gives us alpha. All right, so if we want a 90% confidence level, that means that 90% of the area is going to fall in between these two values. So we're going to have 90% of the area in the middle. Well, if 90% of the area is in the middle, then that means 100% minus 90% is 10%. And this is what we call alpha, 10% or 0.10. So since this is, we want to be centered on the curve here, so 10% cut in half is going to be 5%. We're going to have 5% of the area on the outside of our second value. Let's say our two values are x1 and x2. And we're going to have 5% here. Or in general, we're going to have alpha divided by 2 area out here. Alpha divided by 2 area is out here. All right? So that's what alpha means. So, all right, how do we find these alphas? Okay, well, again, if we have a confidence level of 90%, then our alpha is 10%, because 100 minus 90 is 10%. Half of alpha is 5%. Okay? And so on and so forth for other ones. What we're going to want to find is the z value for this right here. Okay? And if we go look it up or use our calculator, if we use inverse norm, of 0.05, that's going to give us 1.645. Now it's actually going to give you, when you punch in your calculator, it's going to give you negative 1.645 because we have 0 in the middle. That's 0 standard deviations, and that's our mean. And then out here, this is going to be negative 1, negative, let's see if we can write, negative 1.645 standard deviations, and this is going to be 1.645. All right, if we use our z table, so z table, we're looking for an area of 0.05. So we got to look down through our table, 0.05. Oh, there's 0.548, 0.537. We're looking for exactly 0.5. Well, here is 0.505 and 0.495. Now exactly 0.5 falls right in between these two, 0.500. Okay, or you can think of this as, 505, 495. Exactly in between that is 500, 0.500. Okay, so that falls right in between. Well, where are we here? Well, we're at 1.6, and this is at 4.04, and this is at 0.5. So right in between would be negative 1.64, and we're halfway in between 5, 1.645. And that's what we said here. All right. So these values we'll see often. Okay, we have an alpha score of 1.645 for 90% confidence level. Okay, for a 95% confidence level, we're going to have a Z value of 1.96. 98 confidence level, we're going to have a Z value of 2.326, so on and so forth. These values are the locations of these X's, and notice they're getting farther away from the middle. 1.6, 1.96 is out here, 2.3, 2.56. Okay, so it's going to include more area in the middle as we have a higher confidence level. All right. So you can look up the table there and the Z-score. You can use this little shortcut to get that. All right, we're going to need that here in a bit. We can also use inverse norm, like I mentioned there, to get that. This would be inverse norm of 0.05, and this would be 95, because that's 1 minus 5%, or 100% minus 5%. Inverse norm of 0.95. All right, so let's use some of that. Okay. So for a simple random sample of size n, the sampling and distribution of p hat is approximately normal, and that's important. It's approximately normal, meaning that we can use normal distribution stuff. And these formulas are the key. The mean of all the p hats is going to be p. It's what we expect, the population proportion. And the standard deviation can be found using this formula. P, the given proportion, times 1 minus p divided by n square rooted. And all of this depends on whether np times 1 minus p is greater than 10. Because if this is true, then it's normal. If this is not true, it's not normal. Our n is not big enough. Okay? All right. So let's apply that a little bit here. So we want to construct a confidence interval here. Okay, and so what we need to do, if we have a simple random sample of size n, we want a 1 minus alpha confidence level. All right, alpha is how far we're from 100%. And we know p. All right, so we have p is a given proportion. Then we can find the lower bound and upper bound by doing this. We can take p hat and subtract z. The z value is the number of standard deviations times the standard deviations. Okay, so a better way of saying this, or a little simpler way of saying this maybe, is p hat minus the z value for alpha over 2 times sigma. And then this is going to be p hat plus z alpha over 2 times sigma. Now, it's not just the regular sigma, it's the sigma of p hat. All right, it's that thing that formula we just saw a moment ago. And the formula is this square root here. So let's find that, all right? So we're going to get this interval. What this means is that if we have a 1 minus alpha times 100% confidence interval, it indicates that that percent of simple random samples of size n from a population whose parameter is unknown will result in an interval that contains the parameter. So that's the probability that if you pick a random sample of size n, that the result will be close enough to that parameter there. Okay? All right. Let's get some numbers going. That'll help. So back to our survey here. All right. So we had our survey about the death penalty question. So we want to obtain a 90% confidence interval for a proportion of registered voters nationwide who are in favor of the death penalty. All right. So first thing we got to do is we got to get our p-hat value, which we already did. It was 1123 divided by 1783 gives us 0.6298. We already found that. Now we need to find out, is this normal? So we need to check n times p-hat times 1 minus p-hat. And the whole point in doing this is to see if our sample size is big enough. All right. Well, how big is our sample size here? Our sample size is the 1783. So we're going to have 1123 n, which is, 1783 times p-hat, 0.6298, times 1 minus p-hat, 0.6298. All right, and if this is bigger than 10, then we have a big enough sample. Now, we can be certain here that we have a big enough sample because that's a huge number, 1783. And we get 415.7. That is much bigger than 10. All right. So, yes, it is normal. So this implies that we have a normal population. That is, the distribution of p-hats will be normal. All right, since it's normal, we can use our z-table, our normal distribution. All right, so we need to define alpha here. So alpha is going to be, we wanted a 90% confidence interval, right? 90% confidence interval. So alpha is 100 minus 90%. And that's 10%. Okay, so alpha is 10%. Alpha over 2 is going to be 5%. Half of that alpha. So we need to find z of alpha over 2. And that's just the z value for 5%. 0.05. Okay, now we can go look that up in our table, or we can use inverse norm of 0.05. We're going to get that 1.645, okay? So there's a positive version, there's a negative version, all right? We actually, at this point, don't really care about the negative, all right? So we can just kind of ignore that negative if it will go away. Now we can calculate the lower and upper bounds, all right? So we're going to do that using our formulas up here, okay? Now, let's go ahead and calculate the standard deviation separate, because that formula will be a little less confusing if we do that. Okay, so let's go ahead and get our standard deviation of the p-hats. And that formula from the other page is p times 1 minus p all over n, the square root. Okay, and that's just this value right here. Okay, p-hat technically, because it's our point estimate. All right, so that's going to be the square root of our 0.6298. 0.6298 times 1 minus 0.6298. Good to keep lots of decimals there, all over n, which was 1728. And that's going to give us about 0.116. Okay, so that's our standard deviation. So what we're going to do to find our interval here is we're going to take our point estimate, points, then we want to get our lower and our upper values. We're going to take our point estimate, 6298, and we're going to add, we have our z value. What was our z value again? Our z value here was 1.645. That's how many standard deviations we're going to add, 1.645. We're going to add that many standard deviations, and the standard deviation is 0.116. So this is the number of standard deviations, and we found out that this is the size of the standard deviation. Okay, and that gives us 6488. Okay, and actually we need to round that. We should round that a little smaller because notice we only use 3 decimal places here. We use 4 here. We can't trust much more than 3 at this point. Okay, every time you do a calculation, your value is a little less exact if you're using rounded values, and we are. So so we had the plus. Oh, you know what? I'm sorry, we did that backwards. This should have been the minus, because lower is going to be a minus. Upper is going to be plus. So notice the only difference is for the upper, we're going to add 1.645 standard deviations. And that's going to give us our 0.649. And this is going to be minus. So once you do 1, just hit second entry in your calculator, because hopefully you entered that whole thing together. Okay, type this whole thing in your calculator. And the minus version gives us 0.6107, which we'll round up to 0.611. Okay. So what just happened? We found, based on the alpha level, which came from 100 minus 90%, that gave us the z value, the number of standard deviations. We found what a standard deviation is worth here, and we added and subtracted those standard deviations. Is that many standard deviations? And it gives us these two numbers, 0.61 and 0.65. We really are only accurate to maybe 2 decimal places here. Can't really trust that last number because we did so many calculations. So we can be 90% confident. Our last step is to state our solution. We are 90% confident that the proportion of registered voters who are in favor of the death penalty for convicted murder is between 0.61 or 61% and 65%. Okay, so we can be 90% confident that the real value falls between there. Okay, now there is a shortcut. You can also use the TI-84. We won't do that right now, but under stat test and one prop z interval test, you can do that. You can enter our p hat and the values up top here, and it'll find those for you. But this gives us more understanding doing this. All right. So what we just found was this margin of error. It was in the middle of all that. That z value times the standard deviation, because again, this little square root here is just the standard deviation of the p hats. Okay, so z times the number of standard deviations gives us that error, how much we went up and down. Okay, so if we take the same situation and we want to find the margin of error for that 90% confidence interval. Well, the error is just what we added and subtracted. Okay, so we have a p hat of 0.63. We know that the z value was 1.645. And we also found out that the standard deviation, which is the square root of p times 1 minus p hat, all over n. was 0.0116. So our error was just what we added and subtracted. So the margin of error, the amount that we added and subtracted, was our z value, 1.645 times that standard deviation. And that's what this formula up here is saying there. That's z value times the standard deviation. We just kind of did it in two parts. It's helpful since we already did this. And that gives us 0.019, or about 0.02. All right, so we have that margin of error. And looking back at what our interval was, 0.61 to 0.65, notice 0.63 was right in the middle. So 0.63, 63% plus 2% is 65. Minus 2%, so this is plus 0.02, minus 0.02 gives us 61. Okay, so the error, the margin of error is 0.02. Okay. All right, let's go one more and call it good here, right? So how do we find the sample size? How big is big enough? All right, so here's a formula that we can use if we know the value of p hat and we want to figure out how big a sample size we should use. We can use this formula if we have a good estimate for p hat. P hat times 1 minus p hat times the z alpha over 2 divided by the error squared. Okay, so if we know how far off we want to be, we can use that formula there. Okay, here, if we don't know p hat, we can just let p hat be 0.5. All right, and what happens is this becomes 0.5 times 0.5 or 0.25. Okay, so if we don't know p hat, we can use this here. All right. So let's see how that works. So we got a sociologist wanted to determine the percentage of residents of the of America that only speak English at home. The question here is, what size sample should be obtained if she wishes her estimate to be within 3 percentage points with a 90% confidence, assuming that she uses the 2020 estimate obtained by the Census 2000. So her estimate is 82.4%. So that's our p hat. So we're going to use this estimate. We think that p hat is about 82.4% or 0.824. All right? So what we need to do is we need to find the error. Now the error comes from our problem here. So the error is the how far off we want to be. We want to be off by 3 percentage points. So error is 0.03 or 3%. That's how far off we want to be. We don't want to be more than that. So we know our error, all right? So error is 0.03. Z alpha over 2, well, alpha, since we have a 90% confidence level, alpha is 100 minus 90%, which is 10% or 0.10. Alpha over 2 is 5% or 0.05. And so our z of alpha over 2 is the z value for 0.05, which was the 1.645 we've been using. You can get that from inverse norm if you like. 1.645. Okay, or it was on that table at the beginning. Now we can find p hat. Well, that was given to us, 0.824. Okay, we're using that there. Now we have everything we need to use the formula. So the formula says we're going to take p hat times 1 minus p hat times z over e squared. Okay, so let's go with our p hat, 0.824 times 1 minus 0.824 times the z value, which was 1.645, over the error we want, which is 0.03 squared. And type that all into your calculator at the same time carefully. You use your parentheses and you'll get it. And we should get 436.04, which will round that up. Okay, so because we're rounding it up because we need more than that, and so we'll round that up to 437 people. Okay, so the solution, the sociologists must survey 437 people, randomly selected American residents. All right, that's the idea there. So that formula kind of works backwards to find the number that we need in order to get us given errors. So once we know how precise we want to be, it depends on your situation. Are you just doing a school newspaper article, or are you trying to publish something in a scientific journal? The more accurate you want to be, the smaller you want your error to be, the more numbers you're going to need here. All right? So that's the idea. That's a confidence interval, and that's how we find that margin of error that we add and subtract to get our confidence interval.